everyone, Tina here, and today I'd like to talk about vectors in kinematics. You'll usually encounter this topic during year 2 of your A-level course. This topic includes using the suvat equations with vectors. I'll remind you of what the suvat equations are, I'll show you an additional useful formula to do with position vectors, and then we'll run through some examples. I have made another video about the constant acceleration or suvat equations in year 1, so I'd recommend you watch that video first if you haven't already. As a reminder, here are the suvat equations and what the different letters stand for. No matter what exam board you're using, you should be given the suvat equations in your formula book. Here's an extract from the Edexcel version. Kinematics is just maths describing motion of objects without any reference to forces. Now there is an additional formula which is not in the formula book, which is useful when you're dealing with position vectors, and that is R equals R0 plus VT. This R is your position vector at time t. This R0 is your initial position vector. V stands for constant velocity. T stands for time. Again, this is not in the formula book, so you've got to learn this one off by heart. Let's remind ourselves of what position vectors actually are. A position vector describes an object's position or displacement relative to a reference point, and that's usually the origin. Let's take a look at some examples. Example 1. A boat B moves with a constant velocity. At noon, B is at the point with position vector 2i minus 5j kilometers with respect to a fixed origin O. At 2:30, the boat is at the point with position vector minus 8i plus 10j kilometers. Part A, find the velocity of B. Part A, we're going to use that new position vector formula to help us. And it said R equals R0 plus VT. Now we're told that at 2:30, the boat is at the point with position vector minus 8i plus 10j. So that is the position vector at time t. So we're going to put minus 8i plus 10j there. Initial position vector is 2i minus 5j. Velocity vector is what we're trying to find. But we do know that t is going to be 2.5 because we're going from noon to 2:30. So that means we've got 2.5 hours. So we can write 2.5 v there. If we rearrange this, we can have 2.5 v on this side and then minus 10i plus 15j on this side. If you then divide everything by 2.5, you end up with v equals minus 4i plus 6j, and then the units will be kilometers per hour. And that's it. Part B says find the bearing of the velocity vector. So we now know that our velocity vector is minus 4i plus 6j. So it's a good idea to draw a little sketch of what that would look like. So going up and to the left, that would be 4 units to the left and 6 units up with this as our starting point. Now for bearings, we always want to go clockwise from north. So if that's our north line, the angle we're interested in is this one. Now, because this is a right-angled triangle, we can use some trigonometry SOHCAHTOA to work out this angle, which I'm going to call x. X would be inverse tan of 6 over 4, which works out to be 56.3 degrees. I'm then going to work out this angle here, which I'm going to call y, and that's just going to be 90 take away x. So 90 take away 56.3 gives 33.7. Now we know that blue angle, we can work out the bearing by doing 360 take away that blue angle. 360 minus 33.7 equals 326 to 3 significant figures. There's more than one way of working out that bearing, so just do what makes most sense to you. Part C, find an expression in terms of t for the position of B t hours after noon. So this is wanting a generic expression for the position vector at time t. So once again, we can use that formula, R equals R0 or R0 plus VT. R0 is still 2i minus 5j at noon. And then if we keep it generic, we can put t here and then our velocity vector. So minus 4i plus 6j. We can then expand the second set of brackets, and then we can group together the i and j components. So we can say this is the same as 2 minus 4t I, and then plus 6t minus 5j. And that would be an expression in terms of t for the position vector of B t hours after noon. Example 2. A particle P has velocity minus 3i plus j meters per second at time t equals 0. The particle moves with constant acceleration a equals 2i plus 3j meters per second squared. Find the speed of the particle and the bearing on which it is travelling at time t equals 3 seconds. Now, when I read this question, the first thing that comes to mind is that it references constant acceleration, and that is a big clue that you can then use suvat. So if we write down SUVAT, I'm going to give myself a little bit more room than usual because I want to work with vectors in this question. Now, what we want is the speed of the particle at time t equals 3, so that sounds like final velocity. We're told that the velocity is this at time t equals 0. That sounds like initial velocity. Now I'm going to work with column vectors here, but you could also work with the I and j format if you prefer. Acceleration is 2i plus 3j, so as a column vector 2, 3. And time is 3, so t equals 3 here. Displacement, we don't know and we don't care about it, so we can put a cross there. The suvat equation, which does not involve s, is here, and then you can sub in your vectors and work out v. So v equals u plus at, in this context will be minus 3, 1, plus, and then I'm going to put the t in front just to make the calculation a little bit easier. So 3 and then 2, 3 as a column vector. We can then do the calculation. So again, keeping it as a column vector for now, minus 3 plus 3 times 2, so plus 6, and then 1 plus 3 times 3, so 9, gives 3, 10. That's our velocity vector, so that's in meters per second. Again, if you prefer, you could work in IJ format throughout, or you could change it back to IJ format now if you want, so it's 3i plus 10j meters per second. That's just personal preference, up to you. Unless, of course, the question states specifically which format you need to use. Now, that's the velocity, but ultimately in this question, we're actually interested in the speed, and speed is the magnitude of the velocity vector. That's an important fact we need to know. So if we draw our velocity vector here, it's 3i plus 10j, so 3 units to the right, 10 up. The magnitude is just the length of that diagonal line, so we can use Pythagoras to find it. And that's going to be square root of 3 squared plus 10 squared, which is root 109, approximately 10.4 meters per second to 3 significant figures. We also want to know the bearing on which it is travelling. So again, anytime you have bearing, you need to think about the angle clockwise from north. So if we draw our north line on there, we are interested in this angle here for the bearing. Again, different ways of finding this, but I would probably find the angle inside this triangle here first, just using SOHCAHTOA. So in this case, x would be inverse tan 10 over 3, so 73.3. And then the bearing will just be 90, take away that, which is 16.7 degrees, roughly 17 to the nearest whole. And I've done that so I can write it as 017 for a nice 3-digit bearing. And that's it. I just want to go back and emphasize this fact that speed is the magnitude of the velocity vector. That's really important. There's also a similar fact to do with distance. So there's that one, and distance is in fact the magnitude of the displacement vector. So just bear that in mind whenever you see those words speed and distance when you're working with vectors. Last example, at 10 a.m, plane A has position vector 2i minus 5j kilometers and moves with constant velocity minus 4i plus 6j kilometers per hour. Another plane, B, has position vector minus 3i minus 9j kilometers and moves with a constant velocity I plus 8j kilometers per hour. Part A, find the relative displacement of plane A from plane B after t hours. Now, relative displacement of plane A from plane B, you can think about that as wanting to go from plane B to plane A. In terms of position vectors, that's actually going to be RA minus RB. So the position vector of plane A minus the position vector of plane B, both of which are at t hours. So once again, we can use that R equals R0 plus VT formula and work it out for A and B separately. So for RA, initial vector for plane A is 2i minus 5j. Again, I'm going to work with column vectors just because I prefer it. So 2 minus 5 plus, and then keeping t as a generic time for now, velocity minus 4, 6. We can then tidy that up to make it into one column vector, and that would look like 2 minus 4t and minus 5 plus 6t. If we do something similar for RB, so initial vector for plane B is minus 3 minus 9, plus t times B's velocity, which is 1, 8. Again, putting it into one column vector would be -3 plus t and -9 plus 8t. We can now go ahead and subtract them. So if we do that, we're going to get RA minus RB, and that's 2 minus 4t minus 5 plus 6t minus -3 plus t minus 9 plus 8t, and then just carefully subtract. So it's going to be 2 minus 4t plus 3 minus t, because of that minus in between the vectors, and then -5 plus 6t plus 9 minus 8t. Tidying up gives us 5 minus 5t and 4 minus 2t. So again, if you wanted to, you could then write that in IJ format. So that would be 5 minus 5ti plus brackets 4 minus 2tj, and that's kilometers. Just to recap, we found the generic position vectors of A and B separately, and then to find the relative displacement, we did RA take away RB. Part B, find the time when A is due west of B. So questions like this do come up quite often, referencing north, east, south, west. So it may seem obvious to you, but just be sure that you're clear with your directions. So we've got north, east, south, and west. And then if we want to know when A is due west of B, that would be something like this. So A here and B there. So A is directly to the left of B. If you think about it, due west, therefore, means that the j component of the relative displacement would be equal to 0, because there is no displacement in the j direction. They are directly next to each other in that j direction. If we're saying that the j component is going to be 0, that means we can take the 4 minus 2t, make it equal to 0, and solve for t. So in this case, t would end up being 2 hours, and this is after 10 a.m., so therefore 12 p.m. or midday. Finally, for part C, they want the time after 10 a.m. when the planes are exactly 37 kilometers apart. Now that 37 kilometers is referencing a distance, which if you remember from earlier, I said that was the magnitude of the displacement. So if we give that relative displacement from part A a name, let's say we call it vector x, then all we need to do is find the magnitude of that vector x and set it equal to 37. So this is for part C. The magnitude of that relative displacement vector is going to be 5 minus 5t squared plus 4 minus 2t squared, all square rooted. And that's going to be equal to 37. So once again, that's just coming from doing a Pythagoras on the vector to get the magnitude of the vector. To solve this for t, you probably want to square both sides first to get rid of the square root symbol. So if we do that, we're going to get this. And then it's a case of expanding the brackets carefully and then tidying up, preferably into the form of a nice quadratic. Something like this, which you can then solve in your preferred way, for example, using the quadratic formula. Once you solve this quadratic, as expected, you're going to get two t values. One is t equals 8, and the other is t equals minus 5.7. In this context, t stands for time, so any negative time value is invalid, means our only answer is t equals 8. And then don't forget they want the time after 10 a.m. So after 10 a.m., 8 hours after that would be 6 p.m. And we're finished. That's it for now. If you found this video useful, please do remember to like, comment and subscribe to my channel if you haven't already. And do share this with anyone else who you think might find it helpful. Thanks and see you next time.